we were discussing uniform continuity and related concepts, and what we have seen is that uniform continuity is a stronger form of continuity. If a function is uniformly continuous, it is continuous, but the converse is false. What we want to prove next is that if a function is uniformly continuous on a dense subspace, then it can be extended to the whole metric space. Okay. Now in order to prove that, we shall need a couple of things which I will give as an exercise. Okay. Let us say first exercise is the following. Okay. Suppose xd is a metric space. Okay. And suppose you take two sequences xn and yn, both are sequences in x. Okay. And suppose both of them converge to the same limit. Okay. So suppose limit of xn as n tends to infinity is same as limit of yn as n tends to infinity. Okay. Then limit of dxn by n as n tends to infinity, that is 0. Okay. Right. This will follow from an elementary application of triangle inequality. Okay. Right. Okay. Then this second exercise is the following. Suppose there are two metric spaces xd, y rho, those are two metric spaces. Okay. And suppose A is a subset of x, and suppose we take two functions f and g. Okay, let me say functions from x to y, both continuous, f and g functions from x to y continuous. Okay. Then what this exercise says is that if f and g coincide on A, then they coincide on A closure. Okay. So if fx is equal to gx, if fx is equal to gx for every x in A, then fx is equal to gx for every x in A closure. Okay. Okay. As far as the second one is concerned, you can see we have seen that if you take any point in A closure, okay, then you can find a sequence of elements in A. Suppose x is a point in A closure, then there is a sequence xn of points in A such that xn tends to x. If xn tends to x, since f is continuous, fxn tends to fx. Similarly g is continuous, so gxn tends to gx. Okay. And fxn and gxn coincide, so that's the idea in the second exercise. Okay. All right. Now what we want to do is this. Okay. What I mentioned just now. Okay. Suppose that is every function which is uniformly continuous on a dense subset can be extended to the whole metric space as a uniformly continuous function. Okay. So let us say that let xd and y rho be metric spaces, and A a dense subset of x. F from A to y is uniformly continuous. Okay. Then f can be extended to, x as a uniformly continuous function. what is the meaning of saying that f can be extended? It means you can define a function g, let us say a function g which is defined for all values of x such that g is uniformly continuous and gx is equal to fx for x in a, okay. That is the meaning of saying that f can be extended, f can be extended to the whole of x, okay. Alright. Now let us look at the proof. Okay, first let us see how the extension can be defined, okay. As far as it has to be an extension, for the points in a its value has to be fx, right. So let us say define we will construct, let us say define g from x to y as follows. Okay, so what is that? That is g of x is equal to fx for x in a, okay, and we want to say how it is defined for x in x minus a, okay. And for that we use that a is a dense subset of x, okay, is a dense subset of x, okay. Yeah, there should be one more thing that is required here in the hypothesis. This space y must be complete, okay. These are metric spaces and y rho is complete. Okay. And so there are two important assumptions, that is one is that y rho is complete and f is uniformly continuous, okay. Suppose if it is just simply continuous, then also you cannot extend it in general, and if y is not complete, then also this extension is not possible, and that you will see as we go along with the proof, okay. Alright, when we take x in this x minus a, since we know that a is dense in x, every such x will be a limit of a sequence of points in x, okay. So let us just, I will first see how this can be defined, okay. Let us take x in x minus a, okay. Then we can say there exists a sequence of elements in a such that that sequence converges to x, okay. Then there exists a sequence, suppose I call that sequence xn of elements in a such that xn converges to x, okay. Alright, okay. If xn converges to x, in particular xn is a Cauchy sequence, okay. In particular xn is a Cauchy sequence, okay. So then, because we know that every convergent sequence is Cauchy, okay, then xn is a Cauchy sequence, is a Cauchy sequence. Xn is a Cauchy sequence and in A, okay, that is Cauchy sequence in A, and f is uniformly continuous, okay. So we have seen that if xn is Cauchy and f is uniformly continuous, f xn should also be Cauchy, okay. So that implies that f xn is a Cauchy sequence in y, okay, okay, but y is complete, okay. That is where we use this complete, okay. So since y is complete, this f xn should converge to some limit, okay, complete in y, and hence converges to a limit. Suppose I call that limit as y, to a limit say y in y, okay. Then we will define g of x as this number y, okay. we will define g of x as this number y. Okay, so define g of x as limit of f xn. Okay, in this case we call it limit as y. Okay. Now there is a problem with this definition. Okay, and what is the problem? It is that this sequence which converges to x is not unique. Okay, right? It can happen that some other sequence that is given a point in A closure, there may exist several sequences in A which converge to that point x. So suppose you take some other sequence, suppose that sequence is xn prime. Okay, then xn prime also converging to x, then if you follow this procedure, then gx should be defined as limit of f xn prime. Okay, f xn prime. Okay, but then unless we know that these two limits are the same, we cannot say that this is a well defined thing. Okay, this is a well defined element. So to show that the function g defined in this fashion is a well defined, okay, we must show that this g of x does not depend on the particular choice of the sequence xn. Okay, that is the important thing. Okay, so suppose, so to show that g is well defined, okay, to show g is well defined, consider another sequence which also converges to x. Okay, consider a sequence xn prime in A converging to x. Okay. Now this is where I will use this first exercise. Okay. If there are two sequences and if both of them are converging to the same point, then the distance between xn and y, that should converge to 0. Okay, right. So okay, so then d xn prime, this tends to 0. Okay, alright. Now if the distance between xn and xn prime tends to 0 and f is uniformly continuous, so we can show that distance between f xn and f xn prime, that should also converge to 0. Okay, distance between f xn and f xn prime, that should also converge to 0. Okay, this implies that distance between f xn and f xn prime, that also should tend to 0. Okay, okay, but if that is the case, remember f xn prime is also a Cauchy sequence. Okay, right, by the same argument, just as f xn is a Cauchy sequence, f xn prime is also Cauchy, so that also converges to some limit. Suppose that limit is y prime. Okay, then f xn converges to y, f xn prime converges to y prime, and distance between f x, now actually this distance is rho. Okay, because that is in y, and rho f xn prime converges to 0. These things, these three things along with the triangular inequality will imply that y must be same as y prime. Okay, so so using triangular inequality you can show that f xn prime should also converge to the same limit, namely y. Okay, right. So then f xn prime also converges to y. In other words, this limit of f xn does not depend on the choice of that particular sequence xn. Okay. Alright, so let us again recall what we have done. Given any point x outside A, we find a sequence xn in A which converges to x. That sequence is a Cauchy sequence, and hence f xn is a Cauchy sequence, y is complete. So f xn converges to that limit. Okay. Moreover, that limit does not depend on which particular sequence you have chosen. Whichever sequence you choose, the limit of that f of that sequence will be the same. Okay, and that common value is what we take the definition of this g of x for x in x. Okay, so let us say that g of x is limit of f of xn as n tends to infinity, where xn is a sequence in A converging to x. Sequence in A converging to x. And we have seen that this limit does not depend on the particular choice of the sequence xn. So now G is well defined. Okay, now what remains to be shown is that this G defined in this fashion is uniformly continuous on x. That is to show G is uniformly continuous on x. Okay. Now to do that, we know that as far as the set A is concerned, on that set Gx is same as Fx, and that F is uniformly continuous. So we shall use that property. Okay. So let us say that let epsilon be bigger than 0 be given. Okay, and then since F, which is same as G on A, is uniformly continuous on A, there exists okay, since F is uniformly continuous on A, there exists delta bigger than 0, such that if you take 2 points in A with the distance less than delta, the distance between f of those 2 points will be less than epsilon. Okay, so such that for all, let us say for all A B in A with distance less than delta, distance between FA and FB is less than epsilon. Okay, we have to show that the same thing happens for any 2 points in X. Okay, so consider let us say X, and let me say X prime in X, such that distance between X and X prime is less than delta. Okay. Now since X and X prime are in X, there will exist sequences of elements, let us say Xn converging to X and Xn prime converging to X prime, Xn and Xn prime lying in A. Okay, so there exist sequences Xn and Xn prime in A, such that Xn converges to X and Xn prime converges to X prime. Then we know that f of xn, in particular xn is a Cauchy sequence, xn prime is a Cauchy sequence, hence f of xn is a Cauchy sequence, f of xn prime is a Cauchy sequence, and they converge. So let us say that let limit of f of xn be equal to y and limit of f of xn prime, let us say that is y prime, then what we know is that by our definition g of x is y and g of x prime is y prime. Okay. And what we want now is that distance between y and y prime should be less than epsilon. Okay, distance between y and y prime should be less than epsilon. Okay. So now consider rho of y prime. Okay. All right. Now basically again we use the triangular inequality again and again. Okay. So this is what we know is that f of xn prime converges, so f of xn converges to y and f of xn prime converges to y prime. So let us write that, so this is less than or equal to let us say distance between y and f of xn. Okay, plus distance between f of xn and f of xn prime, and finally distance between f of xn prime and y prime. Okay. All right. Now out of these three entries on the right hand side, we know that f of xn converges to y, so this term goes to 0 as n tends to infinity. Similarly, f of xn prime converges to y prime, so this goes to 0 as n goes to infinity. Okay. So only thing remains to be discussed is what happens to this distance between f of xn and f of xn prime. Okay. Right. Okay. All right. But xn and xn prime, those are sequences in A. Right. Xn converges to x and xn prime converges to x prime. All right. Xn converges to x and xn prime converges to x prime. Okay. So we can say that distance between, so these two things xn converges to x and xn prime converges to x prime, from this I can say that distance between xn and xn prime converges to distance between x and x prime. Right. Okay. But distance between x and x prime is less than delta. Okay, distance between x and x prime is less than delta. So we can say that distance between f xn and f xn prime, that should converge to see, remember this f is a uniformly continuous function. Okay, f is a uniformly continuous function. So if distance between xn and xn prime converges to distance between x and x prime, what we must have is that this should imply that rho between f xn and f xn prime, that should converge to some number which is less than epsilon, because what we know is that for each AB with distance between A and B less than delta, see this distance between x and x prime is less than delta. Okay, and this is something that converges to this number which is less than delta. So what we can say is that for large values of n, okay, we can say there will exist some n0, so that whenever n is bigger than or equal to n0, distance between xn and xn prime will be less than delta. Okay, so for those n, this rho of f xn and f xn prime must be less than epsilon. Okay, and that is the argument that we shall use. For large values of n, we know that rho of f xn and f xn prime is less than epsilon. Okay, this happens for all large values of n. We can make this argument more precise. So we can say this happens for all n bigger than or equal to that n0. Which n0? That n0 for which the whenever n is bigger than or equal to n0, distance between xn and xn prime is less than delta. For those n, we will also have rho of f xn and f xn prime is less than epsilon. Okay, in other words, but this is independent of n, this is independent of n, okay. So for those, so we can always choose n which is large enough such that this goes to 0, this goes to 0, and this becomes less than epsilon, okay. Okay, so for large values of f we can say that rho y prime is less than epsilon, okay, right, and this is what we wanted to prove, that is whenever x and x prime is less than delta rho, but what is y is g of x and y prime is g of x prime, okay, right, okay. So that proves that g is uniformly continuous, okay. Now there is one more thing that is dependent on the completeness and uniform continuity. Let us go to the proof of this, okay. And this is a well known application of completeness, okay. You know that in practice several times we need to solve an equation like this, fx is equal to y, okay, okay. And you know that one of the ways of solving this equation is that we convert this equation in the following form, gx is equal to x, okay, right. This can be done in several ways, okay, and this is something you would have learned in numerical analysis, that one of the ways of solving the equation fx is equal to y is convert this into an equation of this form and then find a solution of this, okay. And as you know, solution of such an equation is called a fixed point of g, okay, a fixed point of g. So let us make a general definition. So suppose we take a map f from x to x, okay, map f from x to x, okay, then x naught in x is called a fixed point of f if f of x naught is equal to x naught. Okay. And given a map, what we ask is whether such a map has a fixed point or not, okay. Right. And if we can show that a map has a fixed point, then it is equivalent to say that equation like this has a solution, okay. If this map G has a fixed point, it is same as saying that the equation fx equal to y has a solution, provided you have formulated G in such a way that fx equal to y if and only if gx is equal to x. This can be done, okay. Now what has completeness to do with this, okay. One of the most famous theorem about the existence of a fixed point is known as, okay, let me write here, okay, it is known as Banach's contraction mapping principle, okay, and that is what we shall prove now. It is known as Banach's contraction mapping principle. And the statement of this principle is very simple. By the way, as I have mentioned earlier, Banach is was a very famous Polish mathematician, okay, who has done several things in real analysis and functional analysis, etc. So this name you will come across again and again, especially in the course of functional analysis, okay. So what does this statement say, or what does this Banach's contraction mapping principle say, okay? It says simply this, that is, if you take a complete metric space and if f is a contraction mapping on that complete metric space, then it has a unique fixed point, okay. So the statement is very simple. So let xd be a complete metric space and f from x to x be a contraction or contraction mapping. then f has a unique fixed point. Okay. Now let us look at the proof of this. As you can see from the statement, there are two parts, okay, that there exists a fixed point, okay, and that such a fixed point is unique, right. So we have to prove the existence and uniqueness of the fixed point of this contraction map f. Okay. First of all, let us recall what is the meaning of saying that f is a contraction map. Let us recall what this means. This means that there exists some alpha such that 0 less than alpha less than 1, okay, that is the meaning of contraction, okay? Alpha less than 1 such that distance between, since f is going from x to x, distance between fx and fy is less than or equal to alpha times distance between x and y for all xy in x, right. That is the meaning of saying that f is a contraction, okay, and in particular it means that f is uniformly continuous, right. We have seen that contraction is a special case of uniformly continuous map, okay. We can see first of all that from this it follows in a very more or less trivial manner that if at all a fixed point exists, it must be unique, okay, there cannot be more than one fixed point. How does that follow? Let us say in a way, how does one prove uniqueness? We can just say that assuming that there are two fixed points, we should show that they are the same, okay. So suppose there are two fixed points, okay, suppose I call them x naught and y naught, okay. Suppose f of x naught is equal to x naught and f of y naught is equal to y naught. Then we should show that x naught and y naught must be the same, okay. So consider distance between x naught and y naught, okay. Then distance between x naught and y naught, okay, this must be same as distance between f x naught and f y naught, right, because x naught is f x naught and y naught is f y naught, okay. So this is same as distance between f x naught and f y naught, okay, but f is a contraction, look at this, okay. So this right hand side, this must be less than or equal to alpha times distance between x naught and y naught, okay, right, okay. Now if this is any number bigger than 0, remember alpha is less than 1, okay, alpha is strictly less than 1. So what this means is distance between x naught and y naught is strictly less than distance between x naught and y naught. So that cannot happen unless d x naught y naught is 0, okay, right. So this implies d x naught y naught which is same as saying that x naught is equal to y naught, right, okay. So there cannot exist more than one fixed point, that is clear, uniqueness is clear, okay. So what remains to be proved now is the existence, okay. Now to prove the existence, let us proceed like this, okay. We will start from any point, let us say I will call that point x naught, okay. Let us consider a point x naught, consider point x naught in x, okay, and then define x1, define x1 is equal to f x naught, then x2 is equal to f x1, etc. Okay, right. Define, start from any point x naught, define x1 is equal to f x naught, x2 is equal to f x1, then x3 is equal to f x2, etc. In general, proceeding like this, define xn plus 1 is equal to f xn. Okay, this gives a sequence, right? This gives a sequence. Okay? Our idea of the proof is to show that this sequence is convergent. Okay, we will show that this sequence xn is convergent. Okay, okay, so we shall claim xn is a convergent sequence. Is a convergent sequence. Okay. Once we show that xn is a convergent sequence, okay, then existence of a fixed point will be proved. Okay, the idea is that once we show it is a convergent sequence, it has some limit. Okay? Suppose that limit is x, okay, then, or let us say that limit is x star, okay, then we will show that that x star is the required fixed point. Okay, so we shall prove this claim afterwards. Okay, suppose this claim is proved. Okay, suppose this claim is proved, then how does one complete the proof of the theorem? Then xn is a convergent sequence. Suppose xn converges to x star. Okay, then f is a continuous function, so f xn should converge to f x star, then f of xn converges to f of x star. Okay, all right. But f of xn is nothing but xn plus 1. Okay, that is how we have constructed, right? F of xn, this is nothing but xn plus 1. Okay, all right. Now if xn converges to x star, what about xn plus 1? Xn plus 1 should also converge to x star. Okay? So xn plus 1 should also converge to x star. That means f of xn also converges to x star, and f of xn also converges to f of x star. So what does that mean? It means that f of x star must be same as x star. Okay, right. So whatever is the limit of this sequence, okay, that is a fixed point of the map f. That is clear. Okay, so the only thing remains to be now shown is the proof of this claim. Okay, we must show that the sequence xn is a convergent sequence. Okay, but for that we use the fact that this is a complete metric space. Okay, so what is the way of showing that a sequence converges in a complete metric space? We show it is a Cauchy sequence. Okay, so we shall show that the sequence is a Cauchy sequence. Okay, all right, and let us see how that can be shown. And to do that, we shall again use the fact that this is a contraction mapping. Okay, all right. To do that, let us consider the following. Okay, consider distance between xn plus 1 and xn. Okay, all right. Now xn plus 1 is same as f of xn, and similarly xn is same as f of xn minus 1. Okay, so this is same as distance between f of xn and f of xn minus 1. Okay, all right. But what about that? Look at this. Okay, distance between f of xn and f of xn minus 1, this should be less than or equal to alpha times distance between xn and xn minus 1, okay. So this must be less than or equal to alpha times distance between xn and xn minus 1, okay. So what did we prove? Distance between xn plus 1 and xn must be less than or equal to alpha times distance between xn and xn minus 1, okay. I can use it once again. Distance between xn and xn minus 1 must be less than or equal to alpha times distance between xn minus 1 and xn minus 2, okay. So I can say that this is less than or equal to alpha square times distance between xn minus 1 and xn minus 2, okay. We can go on like that, okay. And finally this will be x less than or equal to alpha cube times distance between xn minus 2 and xn minus 3, etc. Going on like this, lastly we shall reach distance between x1 and x0, okay. Only question is what is the power of alpha here, that we will get, okay. What is the power of alpha? Alpha to the power n minus 1, right, alpha to the power n minus 1, okay. Okay. So given any n, what we have shown is that distance between xn plus 1 and xn should be less than or equal to alpha to the power n minus 1 into distance between x1 and x0, okay. Of course that still does not prove that xn is a Cauchy sequence, okay. What this will certainly prove is that this will go to 0 as n goes to infinity, okay, because alpha is less than 1, okay, alpha is strictly less than 1, okay. But that is not sufficient to show that it is a Cauchy sequence. To show that it is a Cauchy sequence, we must estimate distance between xm and xn, okay, and we should show that that goes to 0 as m and, or that can be made arbitrarily small when m and n are large, okay. So let us do it that way. So now instead of considering xn plus 1 and xn, consider distance between xm and xn, okay. Now of course we should, if m and n are, if m is same as n, this is 0, so there is nothing, okay. So consider m and n to be different, okay. If m and n are different, one of them is bigger than the other, okay, right. So suppose m is bigger than n, suppose m is bigger than n, okay. Bigger than n means what? It should be n plus something, okay, n plus 1, n plus 2 or something. So if m is bigger than n, I can write m is equal to something like, let us say n plus k, okay, m is something like n plus k, okay. So this is same as distance between xn plus k and xn, okay, alright, okay. I will say that this is less than or equal to, see it is difference between distance between xn and xn plus k, okay. This will be less than or equal to distance between xn and xn plus 1, xn plus 1 and xn plus 2, etc., etc., and finally xn plus k minus 1 and xn plus k, okay. So we can say that this is less than or equal to distance between, that is use triangle inequality k times, okay, use triangle inequality k times. So this is less than or equal to distance between xn and xn plus 1 plus distance between xn plus 1 and xn plus 2, etc., okay. Final number should be distance between xn plus k minus 1 and xn plus k, okay. Now for each of these numbers on the right hand side we have estimates here, okay, right. So this number distance between xn and xn plus 1, we have shown that that is less than or equal to alpha to the power n minus 1 into dx x naught, okay. So this number is less than or equal to alpha to the power n minus 1 into dx1 x naught. Okay. What about this xn plus 1 and xn plus 2? Again this by the same argument, that should be less than or equal to, instead of n minus 1 it will be n. Okay. So this will be less than or equal to alpha to the power n dx1 x naught. Okay. The next will be less than or equal to alpha to the power n plus 1 into dx1 x naught. Okay. And going on like this, this last will be less than or equal to, what about this? Okay. Alpha to the power n plus k, right, n plus k, alpha to the power n plus k into dx1 x naught. Okay. So this dx1 x naught is a common number, right, dx1 x naught is a common factor. So dx1 x naught into alpha to the power n minus 1, in fact alpha to the power n minus 1 is also a common factor. Okay, right, alpha to the power n minus 1 is also a common factor. So this is equal to alpha to the power n minus 1 into dx1 x naught into what remains inside, it is 1 plus alpha etc up to what will be the last thing, alpha to the power k plus 1. Okay, alpha to the power k plus 1. Okay. Okay, all right. Now what can we say about this sum 1 plus alpha extra plus alpha to the power k plus 1? It's a geometric progression with common ratio alpha, so that is same as 1 minus alpha to the power k plus 2 divided by 1 minus k, right. So this is okay, so let us say this is nothing but, okay, this number alpha to the power n minus 1 into dx1 x naught multiplied by what, 1 minus alpha to the power k plus 2 divided by 1 minus alpha. Okay. Okay, all right. Now the whole idea is this, what we want to show is that this distance between xm and xn can be made arbitrarily small for large values of m and n. Okay, that is the meaning of showing that xn is a Cauchy sequence. If m and n both are large, it is same as saying that m and k, m is n plus k, it is same as saying that n and k both are large. Okay, right. So if k is large, this number alpha to the power k plus 2 goes to 0, alpha to the power k plus 2 goes to 0, and alpha to the power n minus 1 also goes to 0, right, alpha to the power n minus, see, saying that m and n both are large is same as saying that n and k are large. So in other words I can say that this goes to 0 as n and k tends to infinity. Okay, as n and k tends to infinity, this tends to 0, or which is same as saying that n and k tends to infinity is same as saying that m and n k tends to infinity. In other words, we can make this argument quite precise and say that given epsilon bigger than 0, we can find some n0, so that whenever m and n is bigger than that n0, this distance between xm and xn will be less than this number, which will be less than epsilon. Okay, so that shows that xn, okay, I will come back here, that shows that xn is a Cauchy sequence. Okay, thus xn is a Cauchy sequence. Okay, all right, and that was the, okay, xn is a Cauchy sequence and x is complete, so this implies that xn converges. Okay, that completes the proof of the claim, okay, that we wanted to show that Xn is a convergent sequence, and we already shown that once we show that Xn is a Cauchy sequence, Xn converges, and once we show Xn converges, suppose Xn converges to X star, we already shown that that X star is a fixed point of this map F, okay, and that completes the proof of this theorem, okay. We will stop with that here.